Hey there, folks. I wanted to record a short video recapping Worksheet 5, just to help make sure everyone gets the punchline of this whole part of the worksheet. Um, this is, I think, really important and really relevant to all of our lives because part of the case of that paper we read, that Althouse and others paper, is that in order to understand COVID-19 transmission, you really can't think in averages. And that's a very fundamental part of how COVID operates, that it's very much a disease that tends to spread in a non-average way. And so let's pull that apart by starting to look at this particular figure. So this is something that by the end of Worksheet 5, Part 3, hopefully all of you managed to reproduce. So these are results coming out of the branching process model that we put together, that we modified, that we ran. And now we want to try to understand some of these results that we can see here. And the place I want to start is with understanding the difference between the blue and the purple curves. So just as a quick reminder, on the vertical axis here, we're showing the current number of infected at any point in the simulation. We always start out with just one infected individual, and we step forward discretely according to all these time steps. Some people call it a generation. It's essentially a time step. And so we're seeing here that we start with one infected individual. We have all these different realizations. Many different random things could happen. And we have these summary quantities. So we've got that blue curve and that purple curve. And in this particular case, they're very close together. This is coming out of the model that uses a Poisson distribution for secondary cases. But down here, we can see that those blue and purple curves are actually quite well separated. So what's the difference between those two? Well, they're both averages, but they're averages over a different set of realizations. So these purple curves do not include realizations that did not take off, whereas the blue curves do include all realizations. So what we're seeing here is that, at least for this model where we're using a Poisson distribution under the hood to determine the number of new infections at each time step, it doesn't make that big a difference whether or not we include those non-takeoff cases. But for the negative binomial case, and this is the model we're using to represent COVID, it makes a huge difference. We see there's a huge difference between the number of infected, the mean number of infected persons, depending on whether or not we include these non-takeoff cases. So why do some outbreaks not take off? And what do I even mean by takeoff? Well, here are the probability distributions for secondary cases according to our two different models. We have our Poisson distribution, that's this one here, that's the one labeled independent infections. And we also have our negative binomial model right here. This one is labeled as SSE, super spreading event driven infections. This is also the model that we're using to represent the spread of COVID. So why do some outbreaks not take off? Well, it's because both of these models give some possibility of zero secondary cases. So look over here where we have zero secondary cases. We have a non-zero probability according to both models, which means there is some chance that we start with one infected individual, that person recovers, they don't infect anyone else, and so the infection outbreak is over. It didn't spread to anyone else. It turns out, actually, for this negative binomial model that we've set up, the probability of having zero secondary cases is really high. It's about 60%. So this is actually the most likely outcome according to this model. I jumped the gun there a little bit, but the negative binomial model is telling us that actually the most likely thing to happen is zero secondary cases. And this is the model that we're using to represent COVID-19. Althouse and others actually did a fair amount of statistical study in order to support the choice of using this kind of negative binomial model. So at least at the moment, I'm not trying to justify whether or not this is a good model. That's something Althouse and others do in their paper. At this point, we're just trying to understand what it means for a disease to follow this kind of behavior. So if COVID-19 operates in this way, if most infections don't lead to any secondary cases, how does COVID-19 spread at all? Well, the answer to that is that COVID-19 is driven by super spreading events. Those are events that you've probably heard a lot about just in the news, but what a super spreading event is this kind of secondary case phenomenon where one initial infected person ends up infecting a very large number of additional persons. So in terms of where the super spreading events are on our plot, it's over here in the tail. It's over here where we're looking at larger and larger numbers of secondary cases. Say, maybe I could highlight, say, 6 and 7 as being super spreading events as well. In the review, in the Althouse paper, they actually review a number of different basically episodes. There's things that show up in the news, case studies, and they point to one event in Korea where supposedly one infected individual ended up giving rise to 5,000 secondary cases, so an enormous number of additional infections. So there's a contrast between the Poisson model and this negative binomial, or the model that we're using for COVID-19. In the Poisson model, most of the cases, most of the secondary case values that we end up seeing coming out of this model end up being close to average. We can see that the probability peaks around here. Our mean of this distribution, actually for both distributions, is around 2.6. So we're seeing that we're landing typically close to that 2.6 number. What that means is when we take this Poisson distribution and use it within the branching process model, we'll tend to see things land close to what we call this theoretical curve. This red dashed line is where we assume that every case gives rise to the average number of cases. And what we can see is that if we take an average over the results actually coming out of the branching process model, those averages land close to this theoretical curve. It drops off once we end up running out of susceptible individuals, but at least for a while, it tracks pretty closely to this theoretical one, this simple deterministic model. But the COVID-19 model is very different. In the COVID-19 model, the average very rarely happens. The thing that happens most often is roughly 60% of the time, no additional persons get infected. But when people do get infected, there's usually a large number of infections that happen simultaneously. And so that's how this COVID-19 model can start from, say, one infected person here to a very large number of infected individuals just at that first time step. Note that in the Poisson model, we don't see any realizations that do that. So it is this phenomenon, this fact that COVID-19 is very non-average. It's very, the dynamics tend to be very extreme, either with nothing happening or something very bad happening. We tend to see that if we look at the curve, only looking at cases where infections took off, we can actually get results that are quite a bit more extreme than, say, averaging over all cases. So this red dashed line actually gives us a nice way to compare between both of these two plots because it's identical. It's using that same 2.6 secondary case, average secondary case number. We can see that if we focus in on just those infection outbreaks that take off, well, we end up with quite a few more infected individuals as compared with the trends that we tend to see out of the Poisson model. So what that tells us is that average behavior, that might be good enough to understand some diseases. But when it comes to COVID-19, you simply can't think about the disease when thinking only in terms of averages. So when it comes to understanding the transmission of COVID-19, you can't think only in terms of averages. You actually have to think in terms of variability.